Let's now take a look at the multiplication of this form. So let's say we have x minus a1 times x minus a2 times x minus a3. If you work this out, so you can make this multiplication, what you will find is x to the power 3 minus a1 plus a2 plus a3 times x squared plus a1 a2 plus a1 a3 plus a2 a3 times x minus a1 times a2 times a3. So here we had x minus a1, x minus a2, x minus a3, so we have three roots. What we see is that x to the power 3 has a coefficient of 1, so nothing special. The coefficient of x squared is the sum of all the roots, so it's a1 plus a2 plus a3 with a minus sign. Then the next coefficient x, there we have a multiplication of two roots and we have a sum of all those multiplications. So a1 with a2, a1 with a3 and a2 with a3 with a plus. And then the final one, the constant term, is the multiplication of all the roots together. So a1 times a2 times a3 with a minus. So what we see is that we have alternatively plus, minus, plus, minus. And for the roots, we see that we first have a sum, then we have a sum of a multiplication of 2, then we will get a sum of the multiplication of 3, and if we have more than 3 roots, we get a continuation of this process. So a sum of a multiplication of 3 roots, sum of a multiplication of 4 roots, and so on, until we have used up all of the roots. So this means that if we have a polynomial f of x, which is equal to x to the power n, so the first one always has to be with a coefficient 1, so it has to have a leading term of 1, plus p1 times x n minus 1, plus p2 times x n minus 2, and so on, until the end, plus pn. And if we know that the roots are alpha 1 to alpha n, so alpha 1 up to alpha n are the roots of f of x, then we see here from the previous example that p1 is the sum of all the roots, so it is a sum of alpha I is 1 up to n, but with a negative sign. p2 is a sum of multiplication, so it's a sum of alpha I times alpha j. I and j are different, with a positive sign, so we have a plus. p3 is again a negative sign, and now we will have a multiplication of 3 different roots, so alpha I times alpha j times alpha k, which are all different, and so on. So we have this up till p of n, which is the product of all the roots. It's alpha 1 times alpha 2 times alpha n. And then the sign will depend on the power of n. So it's minus 1 to the power n, because we have alternatively a minus and a plus sign. Or you could also write this as the sum of all the roots is equal to minus p1, the sum of all alpha I times alpha j. So the sum of the multiplication of two roots is equal to p2. If you do it with 3 alpha I, alpha j, alpha k, you take the sum of those, then you get minus p3, and so on. And then in the end, the product we write with pi, I is 1 to n, of alpha I is minus 1 to the power n times pn. So we now have a property which relates the roots of the polynomial to the coefficients of the polynomial. So we have expressions of the coefficients in function of the roots. We thus see that here we have n equations with n unknowns, so alpha 1 up to alpha n. So if my coefficients are given, I have n equations with n unknowns, and so in theory I can solve this system of equations. So based on the coefficients of my expression, I would be able to find the roots, n equations, n unknowns, and we can then solve this system. One remark. We saw that this property only holds if the leading term of f of x is 1. So f of x has to start with x to the power n plus some other terms. Now what happens if this is not the case? So let's say that f of x is an times x to the power n plus an minus 1 x to the power n minus 1 plus until we get to a0. And in this case, an is not equal to 1. The solution is quite simple. You first divide out an. So you get some f1 of x, which is x to the power n plus an minus 1 divided by an times x to the power n minus 1 plus up to a0 divided by an. So now here for f1 the leading term is again 1. So now you can apply the previous property. In this property, this is P1, this is Pn. So we get that P1, which is an minus 1 divided by an, is minus the sum of all the roots. P2, which is equal to an minus 2 over an, is the sum of all products of two roots, so alpha I times alpha j, with I different from j, and so on, up to Pn, which is a0 divided by an. This is just the product of all the different roots, so it's a product alpha I is 1 to n. And of course this one has to be multiplied by minus 1 to the power n to get the correct sign. So this then means that an minus 1 is minus an times the sum of all the roots. An minus 2 is an times the sum of the product of two roots, and so on, until a0 is minus 1 to the power n times an times the product of all the roots. So again, we have now n equations with n unknowns. The unknowns are alpha 1 up to alpha n. The an, so a0 up to an, they are known. We can just read them in the expression of our polynomial. So we plug them in. So we have n equations with n unknowns, and we can apply, or we have applied the property in the same way. So the only difference now is that here the leading term is an, which is not equal to 1. And so here we also get multiplications with an, because we have to take this leading term, which is not equal to 1, into account. How can we then apply this property? So it's a very important property. Because of its applicability, it's very useful to know this property. So let's say that we have an equation x to the power 3 plus 2x squared minus 3x minus 1 equal to 0. And this one has roots alpha, beta, and gamma. Then the question is, find the value of alpha squared plus beta squared plus gamma squared. So find the value of the sum of the squared roots. What you could do is find all the roots separately. So you could find alpha, beta, and gamma and then plug them in. But there is an easier way using the property. So if you find the alpha, beta, gamma separately, you plug them in, the answer is still correct. But sometimes this might be a long way for something that can be solved a lot shorter. We see that for this equation, the leading term is 1, and so we can immediately apply the property. So according to the property, this is P1, this is P2, and this is P3. So P1 is equal to 2, P2 is equal to -3 and P3 is equal to -1. Then, according to the property, we know that the sum of the roots, so the sum of the roots is alpha plus beta plus gamma, is equal to -P1. The sum of a product of two roots, so alpha beta plus alpha gamma plus beta gamma, is equal to P2. And then we also know that the sum of all the products of three roots, so in this case it's just alpha times beta times gamma, is -P3. So -P1 is -2, P2 is -3, and -P3 is 1. This gives me three equations with three unknowns, alpha, beta, and gamma. I could solve it to alpha, beta, and gamma, but it might take me a while to find a solution. There is an easier way by just looking at what we want to find. We want to find alpha squared plus beta squared plus gamma squared. What we will do is we will relate this to special products or special powers. For example, in this case we have squares. What we know is that alpha plus beta plus gamma squared, this is alpha squared plus beta squared plus gamma squared minus the double products. So this is the same, minus 2 times alpha beta minus 2 times alpha gamma minus 2 times beta gamma. So this is alpha plus beta plus gamma squared minus 2 times alpha beta plus alpha gamma plus beta gamma. Then we know that alpha plus beta plus gamma was -2. So -2 to the power 2. And -2 times the sum of all the products of 2, which is -3. So we get here 4 plus 6, or this is equal to 10. So you see that you can easily find the solution to the value alpha squared plus beta squared plus gamma squared by just reasoning with the property. I have my property, I identify the different coefficients, and then I relate them to the roots. And then for the final answer, what I will do is just use basic properties of calculation, of calculus, to find an easy way to find what we need to find. So to find an easy way to solve alpha squared plus beta squared plus gamma squared. Let's take a look at one more example. Assume that alpha, beta, and gamma are the roots of the following equation. So the roots of x to the power 3 minus 6x squared plus 11x plus 6 equal to 0. And what we want to find is the expression alpha divided by beta gamma plus beta divided by alpha gamma plus gamma divided by alpha beta. When we look again at the equation, this is monic, so the leading term is 1, which is okay. Then we have that alpha plus beta plus gamma. According to my property, this is equal to 6. Alpha beta plus alpha gamma plus beta gamma is equal to 11. And the product alpha times beta times gamma is equal to -6. What we then have to do is to reform, so transform this expression. So we have alpha over beta gamma plus beta over alpha gamma plus gamma over alpha beta. And we want to find this expression in an easy way. The easiest way is to first put everything on the same denominator. So this is alpha, beta, gamma. This then gives me alpha squared plus beta squared plus gamma squared over alpha times beta times gamma. We then use the same thing as in the previous exercise. So this is alpha plus beta plus gamma squared minus 2 times alpha beta plus alpha gamma plus beta gamma divided by alpha beta gamma. We plug it in. Alpha plus beta plus gamma is the sum, so this is 6 squared minus 2 times 11 divided by -6. So it is 36 minus 22 over -6 minus 14 over 6, or -7 divided by 3.